Alright, let's get into this then. So we're bringing back Newton Maths, Unit 14, further stats. You all did terribly, so let's go through this then. Sample, once again, is the idea that we're only going to question a certain number of the population, like 10%, let's say, whereas a census means we're asking everyone. So one reason might be it's going to be cheaper. It's going to be cheaper to take a sample, right? If you're asking less people, then that's going to save you money, right? It's also going to be easier. Okay, it's pretty much impossible to ask everyone in the country a question. So, yeah, it's just not really practical. We can try. The government does it every few years, but let's not worry about that. Right, B, they want to take it from a school. As soon as they start talking about like one specific area, this is going to introduce bias. So no, this is bias. Maybe school children are more likely to like chocolate. Okay, school children are more likely to have preference. Something like that, right? Like if you're trying to do a sample on members of the public, you can't just be asking a school, you need to be asking adults, you need to be asking retired people. None of those can be asked in a school setting. Right. Question 2. 1,200 students. We know that we've taken a sample of 25 and 13 out of 25, for example, said they like to watch musicals, so let's just times that by 1,200. Let's type that into a calculator. 13 over 25 times 1,200 gets me 624 students. That's a strange looking too. 624 students. For part B, we've assumed that this sample is representative of the whole population. Sample is representative of the population. Okay, the idea being, once again, this number here, maybe he's only asked students that are part of like a musical theatre group. Maybe they're more biased to want to watch musicals, you know? Something like that. Mrs. Brown, the maths teacher, is absolutely right. Standard is 10%. 10%. So 120 students. That'll do. The idea of 10% being it's still small enough that it's easy, but it's big enough that it's representative of the whole population. Alright, let's go into the actual interesting questions. So we need to create a cumulative frequency graph. So first let's work out the cumulative frequency. The cumulative frequency is going to be 4. 4 plus 11 is 15, plus another 15 is 30, 48, 71. Is that? 71, 88, 100. Okay, added to 100, which is good, because we're on about the masses of 100 octopuses. So that means I need to go up to 100 on my y-axis. So if I started at 0 here, 0, we've got 1 square, 2 square, 3 square, 4 square, 5 square. So I'm thinking like 0, 20, 40, 60, 80. You can see that the final square is actually there, 100. Something like that. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Always a bit of a pain when it's not like perfectly cut out. 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually it needs to be a little bit higher, which is a complete pain. Let's not worry about that too much. Okay, So here we are going to now plot the upper bound of each class against that cumulative frequency. So I'm going to start at 3 on my axes. If you wanted, you could do the whole like squiggly part. I'm just going to start at 3, 4, 5, 6, 7, 8, 9, 10, something like that. Let's draw my axes. This here on my x-axis is my mass in kilograms. So let's write mass kilograms. And this here is my cumulative frequency. Okay. At a mass of 4, my frequency is 4. My cumulative frequency is 4. So at 4, I'm going to go 2 squares to 4. At 5, for example, I'm going to go up to 15. So at 5, let's go to 15. 18, 16, 15 is going to be there. I need to go to 30. 30 is halfway in between. That is there. 7, it goes up to 48. So once again, I'm plotting the upper bound, 42, 44, 46, 40, with the lower, with the cumulative frequency, sorry. Yeah, that's 48. 71, 80, 62, 64, 66, 68, 70, 71 is going to be there. 9 is 88, so just below 90. So that one. 82, 84, 86, 88, this one here. And then the final one is going to be 10, is 100, which is slightly off the graph. A bit annoying. Okay, remember the lower number here, 3, is when we have 0, because nothing was 3 kilograms, so we can put 0 at 3. Okay, which is why it's nice to have 3 on the x-axis. And now a nice smooth curve. Don't do what I'm doing, which is feathering it. Something like that is how our cumulative frequency should look. Okay, so that's part A done. Part B, we're looking for the median mass. If there's 100 octopuses, the median position is going to be 100 divided by 2. Sorry, median position is 100 divided by 2. So that's going to be the 50th octopus. So we're looking for the 50th octopus. So what I'm going to do, at 50, which is here, I'm going to draw a line across and I'm going to figure out how much that octopus weighs. So the 50th octopus weighs roughly, it's a little bit over 7. So let's do something like that. Looks like about 7.1 kilograms to me. Obviously, you can have a range of results. It's obviously got to be more than 7. The reason I'm saying that being, we know that the first 48 was exactly 7. So like at 7 it's 48. So we're above 48, we're at 50. We clearly have to be slightly above 7. So don't put 7 in there. Use a bit of common sense for that. Interquartile range, so let's find the upper quartile. So I'm going to go across at 75. 75 being 78, 76, around here. Dun, 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 dun. Obviously, you can use a ruler as opposed to me kind of eyeballing it. So that looks like 8.2, roughly. So my upper quartile is 8.2. My lower quartile over at 25. 25 is here. Dun, 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 dun. Looks like, what's that, 5.6? Yeah, 5.6. Lower quartile is 5.6. So my interquartile range, therefore, is going to be 8.2 minus 5.6, which is, what, 2.6? Something like that, 2.6 kilograms. Okay. Once again, we include the units where possible. Cool. Now we need to show 60% of the octopuses weigh more than 6.5 kilograms. So let's find out how many octopuses weigh 6.5 kilograms or less. So I'll do that in blue. So this time I'm going to go to 6.5 kilograms. That is here. 1, 2, 3, 4. Yep, there. And I'm going to go up till I hit the line. Okay, which appears to be around 39, I want to say, because it's halfway between the squares. Remember, this 39 means that 39 octopuses, I don't know if that's the right word, but octopuses are less than 6.5 kilograms. So that tells me, so this must mean that 61 or more. 39 or less than, technically, or equal to, /equal to, 6.5. That means 61 or more than that. And since there's 100 octopuses, this here is like 61%. So no, 61% or more. Okay, something like that. Okay, once again, 62, 63, somewhat viable. I'm getting 61%. Okay. Right. This one here, we've got some data. We need to, first of all, complete the table for the women's times. So there are 19 women. First of all, since I have a list of data and it's not like continuous, I need to add 1 to the number of women. So I can find the lower quartile position by doing 19 plus 1 divided by 4. That is 5. So the 5th person in my list is going to be the lower quartile. So let's count. 1, 2, 3, 4, 5. This one here is my lower quartile. That is 17. I've also checked to make sure that the list is in order. It was in order already, so I didn't have to reorder it. If the list wasn't in order, like we'll see later, I would have to spend the time reordering it. Okay, so that's the lower quartile position. The median position is going to be 19 plus 1 divided by 2, which is 10. So the 10th number in my list, 6, 7, 8, 9, 10, is going to be my median. So my median is 22. And the upper quartile position is going to be it's going to be 19 plus 1, and then 3/4 through that. So I'm going to put that in brackets. So 3/4 of the way through that is 15. Like, you could just, think common sense. Lower quartile's 5, median's 10, so it's going to increase by another 5, 15. So I'm looking for the 15th number, 11, 12, 13, 14, 15. 24 is my upper quartile. Okay. Since we are looking at comparing data for part B and C, as soon as we're talking about comparing data, there's only 2 things you compare. You compare an average and you compare a spread. The average we're going to compare, obviously, is the median. So I'm going to say, you can see that the men's median was 24. This here is 24. So men's median was 24 seconds. Women's was 22 seconds. So yes, women were faster, right? If they take less time, that means they were faster. I had a lot of people saying the men took longer, therefore they were faster because the median is higher. If you do something quicker, you are faster. Okay? So that one was comparing the median. C is talking about spread. Now, we don't want to use range. The reason we don't want to use range is because, once again, it gets massively affected by outliers. You could imagine that this 35 here looks like quite the outlier, and we don't want to kind of consider that. So we're gonna use interquartile range. So interquartile range for men. Let's have a look. This is 26. This here looks like 22. So interquartile range of men was 4. whereas interquartile range for women, the difference between here and here, is going to be 7, whereas IQR women is 7. You can just write IQR, you don't have to write interquartile range. No one can be bothered doing that. Interquartile range for women was 7, therefore women were more spread, therefore no. No, women vary more. Okay, if you've got a higher interquartile range, you vary more. Once again, range isn't really allowed here because one person might completely offset the range, whereas interquartile range doesn't get affected by outliers. So make sure we're talking about interquartile range, make sure we're talking about average. I don't care about the smallest value. Once again, that might be an outlier. I don't care about anything but the median for part B. Okay. All right, this one. So we've got the same idea as before. To draw a box plot, we need the minimum value, the quartiles, and the largest value. So let's first of all put this list into order. So 6 is the smallest, 9 is the second smallest, 11 is the third smallest, 14, 15, 15, 17, 18, put commas between each of these, 18 across off, 25, 23, almost missed that, 25, 26, 26, two 26s, 26, 26, 31. Let's just quickly move all of these back to the left. So I've got a bit more room. 31, 32, and 45. Okay. So what's nice to do at this point is we know that there's 15 people, so I'm just going to quickly make sure I've wrote down 15 numbers. That's a nice little way of checking to see if you've not missed any. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Since I've wrote down 15 numbers, it's very unlikely that I've missed one. The only thing being if I've counted one twice, but I don't think I have. Okay, so since there's 15, same idea as what we just did previously. Because it's a list of numbers, I need to add 1. 15 plus 1, so lower quartile position, is going to be 15 plus 1 divided by 4, that is 4. So the fourth number in my list is going to be my lower quartile. So my lower quartile is 14. This is going to be the lower quartile. My same idea, I'm not going to bother writing down the calculations for the rest. The median position is going to be 15 plus 1 divided by 2, which is 8. So the 8th number is my median, 5, 6, 7, 8. So my median was 18, and my upper quartile is going to be 12, right? If it goes 4, 8, obviously it's just doing the 4 times tables. The next one's going to be 12, so let's count to 12. Sorry, what am I doing with the arrows? 9, 10, 11, 12. So my upper quartile was 36. Let's just quite note this down. Lower quartile, upper quartile, not upper quartile, median, and upper quartile. Okay. So we want our numbers to go between 6 and 45. So let's just start at 0 and let's do every kind of thing is worth 10. 0, 10, 20, 30, 40. Let's move all of this down. Obviously I have the luxury of being able to move stuff a bit. Me. 40, 50. Okay, at that point, like, it doesn't really matter, like, I've used it all. Cool. So I need to plot where the smallest is. The smallest is going to be at 6, so 10, 9, 8, 7, 6 here. That's why I don't like working on an iPad. Apparently I've drew an hour of them. That is at 6. My lower quartile is going to be all the way at 14, 11, 12, 13, 14. There. My median is at 18. Not there. On to the left. My upper quartile is at 26, which I think is there. This is why I hate iPads. They try and autocorrect themselves too much. Something like that. My maximum value is at 45. That's all the way over here. 41, 42, 43, 44, 45. If in doubt, just start counting. And then, obviously, do our little boxes. This is a box plot after all. I think this is a box plot. I didn't even read the question. Right. Something like that. Okay. Enough to get you the first set of marks. Now we're told that outliers is defined as 1.5 the interquartile range, either above the upper quartile or below the lower quartile. So let's first of all work out the interquartile range. I'm just going to remove that stuff from the bottom to save a bit of room. You probably don't need to do all that working anyway. So the interquartile range is going to be 18 minus 14, that is 4. Okay, so if I want, oh no it's not, because that's the median, 26 minus 14, that is 12. Well, that sounded wrong. AKA this distance here is 12, right? From there to there. So 1.5 times that, 1.5 times 12 is equal to 18. So I can either be 1.18, below the lower quartile, so either 18 below here. That gets me into the negative, so let's not consider that. Or I'm not allowed to be more than 18 above the upper quartile. So 18 above the upper quartile, 18 above 26, so 26 plus 18, that gets me 44. Do I have a number bigger than 44? Yes, I do. This one right here. 45 is an outlier, because it's more than 1.5 times the interquartile range above the upper quartile. Okay. All right. Moving on. Good old Leo. He's studying the mass of red squirrels. A lot of people did this right, which was nice to see. We can do 14 over n is equal to 6 over 18. So at this point, I can flip both sides over to get n over 14 equals 18 over 6. So n is equal to 42, right? Times by 14. This here is 3, so fine. Okay. So that's A. For part B, we're going to just use the data here. So if we want the median, we need to write it in order, which I understand is a bit of a pain. But we do that because otherwise we start making very silly mistakes, like a lot of you did. So smallest is 284. 287. 288. 289. 290. And once again, this is how I am doing it, so this is how I expect you to be doing it. If I'm having to do it this way and I can't do it in my head, I don't expect anyone to be able to do it in their head. Okay? This isn't about like showing off or anything. This is about making sure we get the answer right. So we're going to take some time to make sure we get the answer right. Okay? 306. 312. Okay. Always write too big, don't I? 312. Did that. 315. 315 again. 319, 321, and 327. Once again, good to always check. Right, there are 14 squirrels, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 numbers, so I'm pretty sure I've wrote them all down. So my median position is going to be 14 plus 1 divided by 2. That is 7.5. So I'm looking for the number between the 7th and the 8th. So let's quickly count. 1, 2, 3, 4, 5, 6, 7, 8. So I'm looking for the number in between those two. That is going to be 304. Median is 304. Okay. Once again, I wouldn't expect you to do this without putting them in order. Like what? It took me like 35 seconds there, and I can guarantee I get it right. The range is going to be 327 minus 284. This is a calculator, so let's just use a calculator. Like, you don't need one for this, but why not use it if you got it? That's 43. Okay, cool. Assumptions we've made. There's, like, you could come up with a lot. For part A, the most common kind of correct answer is no, tags fell off. And we've also assumed population hasn't changed. Okay, now a lot of people kind of wrote, oh, squirrels could have died as one assumption, and squirrels could have been born as a second assumption. That unfortunately falls under the same idea of the population has changed size. So you actually don't get 2 marks, you get 1, but not 2. So population hasn't changed. Off has 2s, hasn't changed. So this is 2 assumptions for part A. You didn't need any more, but if you wanted one for part B, you're assuming that this is it, right? You're assuming that there are no other squirrels like outside this range. So all other squirrels are inside the range. Or that these squirrels here are representative of all squirrels. Squirrels, okay, being the idea. Cool. Right, let's get to the histogram. I think we are almost done now, right? Yep, 2 more questions. So a lot of people did this wrong, which really upsets me. What I'm going to do, I'm going to copy the table down a bit. Let's just copy the table and let's paste it down here. And I'm just going to work with this table. Right, fine. What we're going to do this really tediously. Cool. First thing I'm going to work out for each one is the class width. Class width I get by doing the upper bound minus the lower bound. 2 minus 1.5 is 0.5. 2.5 minus 2 is 0.5. 2.8 minus 2.5 is 0.3. 3 minus 2.8 is 0.2. 3.5 minus 3 is 0.5. And 5 minus 3.5 is 1.5. Okay, so once again, the distance between these two, for example, is 1.5. The distance between these two is 0.2. Now I work out the frequency density. The way I work out the frequency density is I do frequency divided by class width. So I'm going to do 7 divided by 0.5. That is 14. This is a calculator paper. No one should get this wrong. 38. 31 divided by 0.3. I don't know. So I'm just going to type in a calculator. 103.3 reoccurring. 52 divided by 0.2 is 260, which is absolutely disgusting, but we live with it. 34 divided by 0.5 is 68. And 1.5 divided by, 7 divided by 1.5 is going to be 4.666 reoccurring. Okay, cool. So those are our frequency densities. We now need to plot these frequency densities with this class width somewhere on here. So I'm going to try and use the full graph. we need to use as much room as we can in order to do this. So I wouldn't expect anyone not to be using the full bar, okay? So we're going to use the full thing. Right. Now, my kind of... Let's actually do the little line. I need to go all the way up to 260, okay? Now, people were doing really weird scales, like 40, 70, 30, whatever. Always try and go in like 10s or 50s or 100s or something like that, or like 5s or something easy, okay? Don't go in like 30s because that's really hard to think how much is each square worth. If you've only got 10 squares for thing, use those 10 squares fully, right? So we have 1, 2, 3, 4, 5, 6, 7. So I'm thinking if I go up in 50s each time, that will definitely allow me to get all the way up to 260, right? So starting at 0, 50, 100, 150, 200, 250, 300, and 350. This here is my frequency density. Remember that goes on the y-axis. On my x-axis is going to be my classes, so starting here, 1.5, 2, 2.5, that doesn't work. Let's start at 1 instead. I know we don't have 1 on there, but that's fine. 2.2, 3, 4, 5, 6, 7, so on and so forth, right? Cool. Now, we know at 1.5 we have a frequency density of 14. Since there's 10 squares here, each square is worth 5, so 14 is just going to be below 3 squares. So let's go to 5, that's here, and it's going to be just below 3 squares up until 2. I'm not judging you for like how accurate this is as long as you've got the right idea. Okay, it should be just below 3 squares. If it's not the right amount below 3 squares, who cares? Right, 38 is going to be just below 8 squares, and that goes from 2 to 2.5. So just below 8 squares is going to be 2 to 2.5. From 2.5 to 2.8, it should be all the way up at 103. So that's just above 100, but not quite at the next square. So just 100 around there. And that's all the way up to 2.8. I do have the luxury of being able to zoom in, but you have the luxury of having a ruler, so no complaints. From 2.8 to 3 is 260. Now that should be a lot easier to plot. That's going to be 2 squares above 250. Once again, each square is worth 5. Vertically, that's speaking, each square horizontally is worth 0.1. I'm hoping I didn't need to explain that part. I'm sure you're all having great fun watching me make a histogram. 3 to 3.5 is 68, so 68 is going, it's going to be just under like 3 squares above 50, sorry, just under 4 squares above 50, should I say. So around here, and that's going all the way up to 3.5, right? Yeah. Yeah, and then from 3.5 to 5, we're at 4.6, which is actually just below 1 square. I've just noticed that this bar isn't horizontal. So just under 1 square across, all the way up to 5, which is going to look a bit silly, but what can you do? Once again, use a ruler for this. Okay, it's a really weird looking histogram, this, because I'm just going to not have that line there, just so it's easier to read, because this is so much bigger than the rest, but fine, whatever. Okay, if that's what they give us in the exam, that's what they give us in the exam, we have to be able to deal with that. Okay, Now I want to estimate the median length of the dolphins. We know there are 150 dolphins. Since this is continuous data, since I've drawn a histogram for it, then I don't need to add 1 because adding 1 is a pain, right? So this is already even, so let's just divide it by 2. So the median position is going to be 150 divided by 2, which is 75. Okay. Now I know that this here already has an area of 14. This here has an area of 38. So in total, no it doesn't. What am I on about? This one here has an area of 7. Frequency is 7. This one here has a frequency of 19. So in total, 7 plus 19 is 26. Plus another 31 here. Plus 31. That's 57 in total. So these 3 add up to 57. If I add this entire bar on, I'm definitely going to be above 75. So somewhere in here there's going to be a line. Okay, I don't know where, let's just draw a line. Like that. Okay, I've drawn it exactly on the line, it doesn't matter. Such that this area on the left is the remaining to get me to 75. To get me to 75 at this point, I need another 18. So I've got a kind of big rectangle that looks like this, that has an area of 18. We don't know its width, but I do know its height because I know its frequency density, and it's this 103.3 reoccurring. Okay, and we need to use that 0.3 reoccurring, otherwise it's not going to work. So now I can say at this point, x times 103.3 reoccurring is equal to 18. So x is equal to 18 divided by 103.3 reoccurring. If you don't know how to do reoccurring, just type in like 8 3s in a row and it'll give you the correct answer. 0.1741, so on and so forth, 9, ... Don't really care at this point. So remember this here is already at 2.8. So what we're going to do is we're going to have to add that part on. So I'm going to do 2.8 plus this distance x, and that's going to tell me the coordinate of the point here. So 2.8 plus x, 2.8 plus 0.17 is going to be 2, and let's just go to 3 significant figures, 2.97. Okay. Cool. Yeah, happy days. Perfect. We want to estimate how many are more than 3.25 meters. So we are looking for, if you imagine, 3.25 meters is going to be here, right? So we're now looking for everything to the right of that, this entire pink area. Now I already know that this one on the end has 7 in, so I just need to work out this pink area. We know that this section here has a frequency density of 68. If we're going from 3.25 to 3.5 on my x-axis, that's a distance of 0.25. So I've got a horizontal distance of 0.25 with a height of 68. The area of that is going to be 68. Sorry, I know this working is a bit messy. 68 times 0.25. 68 times 0.25 is going to be 17. So this section here has an area of 17. Adding those two together, these two here, gets me an area of 24. Done. Okay. Getting there. Swear we're almost done. Whew. Work out the estimate of fraction of seahorses that have a length between 14 and 16 centimeters. So we need to work out the area of this section here and the area of this section here. Okay, so this has a width of 1 and a height of, I want to say, 9. So 14 to 15 is going to be, that's got an area of 9. And then 15 to 16, once again, it's 1 across and it's 4 up. This has an area of 4. So in total, there are 13 seahorses that are between 14 and 16. And as a fraction of the total, 13 over 50. It is an estimate because we don't know the actual data. And we are assuming it's evenly distributed. Okay, but once again, actually maybe this section here, this section on the right, maybe all the seahorses are actually between 16 and 17, and there are 0 here. There's just 8 of them here, or something. Okay, we don't know. We're assuming that it's evenly distributed, but we don't actually know. Okay. Right. If I wanted a pie chart to represent the seahorse data, we need to figure out the area of each of them. That one's got 8. 10 to 12 is 2 across and what looks to be like 3 tall, I want to say. So that's got an area of 6 here. This one is 1 across and 8 tall, so that's 8. This one is a half across and what appears to be how many tall is that? 24. A half times 24 is 12, and this one is a half across as well, and it appears to be exactly 20 tall. That's 10. Now if I've done everything right, these should add up to give 50, because we know there's 50 seahorses. 6 plus 8 plus 12 plus 10 plus 9 plus 8 gets me 53, so something's definitely gone wrong. Let's just double check that these heights are right. 21, 2, 3, 4, so 24 times a half is 0.5. This one here is definitely 10. 20 times a half is 10. This one here is 8 and 1 across. 8 times 1 is 1. This one here is, strange. I'm getting 53. But it might just be me misreading. Maybe this one is only 2, and maybe this one is a bit lower. I don't know. Okay. If anyone can figure out why I'm getting this answer wrong, maybe you've got something else. How strange. How strange. Right, cool. Let's not bother like caring too much. So let's just plug all of these in. We just can't read it accurately. So let's assume that there are 50 anyway. It's not going to add to 360, but actually, why am I getting? This is annoying me. That's 1.5 times 2, that would be why. So this only has an area of 3. Sorry, I was doing 3 times 2, but it's 1.5 times 2. There we go, that adds up to 50 now. So for 10 to 12, 10 less than x less than or equal to 12 is going to be, we're going to do 3 over 50 times 360. 3 over 50 times 360 is going to be 21.6. For 12 to 13, we're working out the angles here, obviously 12 to 13. We're doing 8 over 50 times 360. 8 over 50 times 360, that's 57.6. So on and so forth. I'm not going to write all the calculations anymore. 13 less than x less than or equal to 13.5. making a lot of mistakes. This is why you don't do stuff at like 9 p.m. Because then you're tired. That's going to be 12, so 12 over 50 times 360. That's going to be 86.4. 13.5x less than or equal to 14 is going to be 10 over 50 times 360. I probably don't need a calculator for that, but 72. Okay, 14 to 15, 14 less than x less than or equal to 15 is going to be 9 over 50 times 360, which gets me 64.8. And finally, 15 to 17 is going to have an angle of, once again, 8 over 50 times 360, which is 57.6. Okay, all very disgusting numbers, very disgusting angles. We hopefully know how to draw a pie chart. We draw a circle, like so. Let's draw a line to the center, something like that. Okay, and then let's just measure the angles. 21.6, probably going to look something like that. I'm just eyeballing it. That's going to be 21.6 degrees, and that is the 10 to x to 12 bit. 57.6, adding those together is slightly less than 90, so something over here. That's 57.6, and that's the 12 to 13 bit. At this point, I think we get the idea, right? 86 degrees, once again, it's just a bit less than 90, something like that. 6.4. You don't need to write the angles on, I'm just writing them on because I don't have a protractor. 13 less than x less than 13.5. 72 degrees, once again just less than 90. All of these seem to be just less than 90. 72 degrees, and that's 13.5. Less than x, less than or equal to 14. 14 to 15 is going to be 64.8, which is something like, probably more like that. Okay, like that. 64.8, and that's the 14 to 15 section. And then this one here is the 57.6 again, which is the 15 to 17 section. Cool. Hopefully that is everything covered. If you've got any more questions, please let me know. Yeah, cool. We will leave it there then. Bye.